Darkness. Far away, hidden from the eyes of daylight, there are watchers in the skies. That was written by Europeties in the backki around 406 BC. As children, we fear the dark. Anything might be out there. The unknown troubles us. Ironically, it's our fate to live in the dark. This unexpected finding of science is only about 3 centuries old. Head out from the earth in any direction you choose. And after an initial flash of blue and a longer wait while the sun fades, you are surrounded by blackness, punctuated only here and there by the faint and distant stars. Even after we're grown, the darkness retains its power to frighten us. And so there are those who say we should not inquire too closely into who else might be living in that darkness. Better not to know, they say. There are 400 billion stars in the Milky Way galaxy. Of this immense multitude, could it be that our humdrum sun is the only one with an inhabited planet? Maybe the origin of life or intelligence is exceedingly improbable. Or maybe civilizations arise all the time, but wipe themselves out as soon as they are able. Or, here and there, peppered across space, orbiting other suns, maybe there are worlds something like our own, on which other beings gaze up and wonder as we do about who else lives in the dark. Could the Milky Way be rippling with life and intelligence, worlds calling out to worlds, while we on Earth are alive at the critical moment when we first decide to listen? Our species has discovered a way to communicate through the dark, to transcend immense distances. No means of communication is faster or cheaper or reaches out farther. It's called radio. After billions of years of biological evolution, on their planet and ours, an alien civilization cannot be in technological lockstep with us. There have been humans for more than 20,000 centuries, but we've had radio only for about 1 century. If alien civilizations are behind us, they're likely to be too far behind to have radio. And if they're ahead of us, they're likely to be far ahead of us. Think of the technical advances in our world over just the last few centuries. What is for us technologically difficult or impossible? What might seem to us like magic might for them be trivially easy. They might use other, very advanced means to communicate with their peers, but they would know about radio as an approach to newly emerging civilizations. Even with no more than our level of technology at the transmitting and receiving ends, we could communicate today across much of the galaxy. They should be able to do much better, if they exist. But our fear of the dark rebels. The idea of alien beings troubles us. We conjure up objections. It's too expensive, some of us say. But in its fullest modern technological expression, it costs less than 1 attack helicopter a year. We'll never understand what they're saying, some of us say. But because the message is transmitted by radio, we and they must have radio physics, radio astronomy, and radio technology in common. The laws of nature are the same everywhere. So science itself provides a means and language of communication, even between very different kinds of beings, provided they both have science. Figuring out the message, if we're fortunate enough to receive one, may be much easier than acquiring it. It would be demoralizing to learn that our science is primitive, some say. But by the standards of the next few centuries, at least some of our present science will be considered primitive, extraterrestrials or no extraterrestrials. Incidentally, so will some of our present politics, ethics, economics, and religion. To go beyond present science is one of the chief goals of science. Serious students are not commonly plunged into fits of despair on turning the pages of a textbook and discovering that some further topic is known to the author, but not yet to the student. Usually, the student struggles a little, acquires the new knowledge, and following an ancient human tradition, continues to turn the pages. All through human history, some of us say, advanced civilizations have ruined civilizations just slightly more backward. Certainly. But malevolent aliens, should they exist, will not discover our existence from the fact that we listen. The search programs only receive, they do not send. You know, surprisingly many people, including New York Times editorialists, are concerned that once extraterrestrials know where we are, they'll come here and eat us. Put aside the profound biological differences that must exist between the hypothetical aliens and ourselves, and imagine that we constitute an interstellar gastronomic delicacy. Why transport large numbers of us to alien restaurants? The freightage is enormous. Wouldn't it be better just to steal a few humans, sequence our amino acids or whatever else is the source of our delectability, and then just synthesize the identical food product from scratch? The debate is, for the moment, moot. We are now on an unprecedented scale, listening for radio signals from possible other civilizations in the depths of space. Alive today is the first generation of scientists to interrogate the darkness. Conceivably, it might also be the last generation before contact is made. And this, the last moment before we discover that someone in the darkness is calling out to us. This quest is called The Search for Extraterrestrial Intelligence, SETI, pronounced SETI. Let me describe how far we've come. The first SETI program was carried out by Frank Drake at the National Radio Astronomy Observatory in Green Bank, West Virginia in 1960. He listened to two nearby sun-like stars for 2 weeks at one particular frequency. Nearby is a relative term. The nearest was 12 light years, about 70 trillion miles away. Almost at the moment Drake pointed the radio telescope and turned the system on, he picked up a very strong signal. Was it a message from alien beings? Then it went away. If the signal disappears, you can't scrutinize it. You can't see if, because of the Earth's rotation, it moves with the sky. If it's not repeatable, you've learned almost nothing from it. It might be terrestrial radio interference, or a failure of your amplifier or detector, or an alien signal. Unrepeatable data, no matter how illustrious the scientist reporting them, are not worth much. Weeks later, the signal was detected again. It turned out to be a military aircraft broadcasting on an unauthorized frequency. Drake reported negative results. But in science, a negative result is not at all the same thing as a failure. His great achievement was to show that modern technology is fully able to listen for signals from hypothetical civilizations on the planets of other stars. Since then, there have been a number of attempts, often on time borrowed from other radio telescope observing programs, and almost never for longer than a few months. There have been some more false alarms at Ohio State, in Arecibo, Puerto Rico, in France, Russia, and elsewhere, but nothing that could pass muster with the world scientific community. Meanwhile, the technology for detection has been getting cheaper, the sensitivity keeps improving, the scientific respectability of SETI has continued to grow, and even NASA and Congress have been a little less afraid to support it. Diverse, complementary search strategies are possible and necessary. It was clear years ago that if the trend continued, the technology for a comprehensive SETI effort would eventually fall within the reach even of private organizations or even wealthy individuals. And also that sooner or later, the government would be willing to support a major program. After 30 years of work, for some of us it's been later rather than sooner, but at last, the time has come. The Planetary Society, a non-profit membership organization that Bruce Murray, then the director of JPL, and I founded in 1980, is devoted to planetary exploration and the search for extraterrestrial life. Paul Horowitz, a physicist at Harvard University, had made a number of important innovations for SETI and was eager to try them out. If we at the Planetary Society could find the money to get him started, we thought we could continue to support the program by donations from our members. In 1983, Andrian and I suggested to the filmmaker Steven Spielberg that this was an ideal project for him to support. Breaking with Hollywood tradition, he had, in 2 wildly successful movies, conveyed the idea that extraterrestrial beings might not be hostile and dangerous. Spielberg agreed. With his initial support, through the Planetary Society, Project META began. META is an acronym for Mega Channel Extraterrestrial Assay. The single frequency of Drake's first system grew to 8.4 million. But each channel, each station we tune to, has an exceptionally narrow frequency range. There are no known processes out among the stars and galaxies that can generate such sharp radio lines. If we pick up anything falling into so narrow a channel, it must, we think, be a token of intelligence and technology. What's more, the Earth turns, which means that any distant radio source will have a sizable apparent motion, like the rising and setting of the stars. Just as the steady tone of a car's horn dips as it drives by, so any authentic extraterrestrial radio source will exhibit a steady drift in frequency due to the Earth's rotation. In contrast, any source of radio interference down here at the Earth's surface will be rotating at the same speed as the META receiver. META's listening frequencies are continuously changed to compensate for the Earth's rotation, so that any narrow band signals from the sky will always appear in a single channel. But any radio interference down here on Earth will give itself away by racing through adjacent channels. The META radio telescope at Harvard, Massachusetts, is 26 meters, that's 84 feet in diameter. Every day, as the Earth rotates the telescope beneath the sky, a swath of stars narrower than the full moon is swept out and examined. Next day, it's an adjacent swath. Over a year, all of the northern sky and part of the southern is observed. An identical system, also sponsored by the Planetary Society, is in operation just outside Buenos Aires, in Argentina, to examine the southern sky. So together, the 2 META systems have been exploring the entire sky. The radio telescope gravitationally glued to the spinning Earth, looks at any given star for about 2 minutes. Then it's on to the next. 8.4 million channels sounds like a lot, but remember, each channel is very narrow. All of them together constitute only a few parts in 100,000 of the available radio spectrum. So we have to park our 8.4 million channels somewhere in the radio spectrum for each year of observation, near some frequency that an alien civilization, knowing nothing about us, might nevertheless conclude we're listening to. What could such a frequency be? Hydrogen is by far the most abundant kind of atom in the universe. It's distributed in clouds and as a diffuse gas through interstellar space. When it acquires energy, it releases some of it by giving off radio waves at a precise frequency. Here's the frequency: 1,420.405751768 megahertz. 1 hertz means the crest and trough of a wave arriving at your detection instrument each second. So 1420 megahertz means 1.420 billion waves entering your detector every second. Since the frequency of light is just the speed of light divided by the frequency of the wave, 1420 megahertz corresponds to a wavelength of 21 centimeters. Radio astronomers anywhere in the galaxy will be studying the universe at 1420 megahertz and can anticipate that other radio astronomers, no matter how different they might look, will do the same. It's as if someone told you that there's only one station on your home radio set's frequency band, but no one knows its frequency. Oh yes, one other thing. Your set's frequency dial, with its thin marker that you adjust by turning a knob, happens to reach from the Earth to the Moon. To search systematically through this vast radio spectrum, patiently turning the knob is going to be very time-consuming. Your problem is to set the dial correctly from the beginning, to choose the right frequency. If you can correctly guess what frequencies the extraterrestrials are broadcasting to us on, the so-called magic frequencies, then you can save yourself a great deal of time and trouble. These are the sorts of reasons that we first listened, as Drake did, at frequencies near 1420 megahertz, the hydrogen magic frequency. Horowitz and I have published detailed results from 5 years of full-time searching with Project Meta and 2 years of follow-up. We can't report that we found a signal from alien beings. But we did find something puzzling. Something that for me, in quiet moments, every now and then, raises goosebumps. Of course, there's a background level of radio noise from Earth. Radio and television stations, aircraft, portable telephones, nearby and more distant spacecraft. Also, as with all radio receivers, the longer you wait, the more likely it is that there'll be some random fluctuation in the electronics, so strong that it generates a spurious signal. So we ignore anything that isn't much louder than the background. Any strong narrowband signal that remains in a single channel we take very seriously. As it logs in the data, Meta automatically tells the human operators to pay attention to certain signals. Over 5 years, we made some 60 trillion observations at various frequencies while examining the entire accessible sky. A few dozen signals survive the culling. They are subjected to further scrutiny, and almost all of them are rejected. For example, because an error has been found by fault detection microprocessors that examine the signal detection microprocessors. What's left? The strongest candidate signals after 3 surveys of the sky are 11 events. They satisfy all but one of our criteria for a genuine alien signal. But the one failed criterion is supremely important: verifiability. We've never been able to find any of them again. We look back at that part of the sky 3 minutes later, and there's nothing there. We look again the following day. Nothing. Examine it a year later, or 7 years later, and still, there's nothing. It seems unlikely that every signal we get from alien civilizations would turn itself off a couple of minutes after we begin listening and never repeat. How would they know we're paying attention? But just possibly, this is the effect of twinkling. Stars twinkle because parcels of turbulent air are moving across the line of sight between the star and us. Sometimes these air parcels act as a lens and cause the light rays from a given star to converge a little, making it momentarily brighter. Similarly, astronomical radio sources may also twinkle, owing to clouds of electrically charged, or ionized, gas in the great near vacuum between the stars. We observe this routinely with pulsars. So, imagine a radio signal that's a little below the strength that we could otherwise detect on Earth. Occasionally, the signal will by chance be temporarily focused, amplified, and brought within the detectability range of our radio telescopes. The interesting thing is that the lifetimes of such brightening, predicted from the physics of the interstellar gas, are a few minutes, and the chance of reacquiring the signal is small. We should really be pointing steadily at these coordinates in the sky, watching them for months. Despite the fact that none of these signals repeats, there is an additional fact about them that, every time I think about it, sends a chill down my spine. 8 of the 11 best candidate signals lie in or near the plane of the Milky Way galaxy. The 5 strongest are in the constellations Cassiopeia, Monoceros, Hydra, and 2 in Sagittarius, in the approximate direction of the center of the galaxy. The Milky Way is a flat, wheel-like collection of stars and gas and dust. Its flatness is why we see it as a band of diffuse light across the night sky. That's where almost all the stars in our galaxy are. If our candidate signals really were radio interference from Earth, or some undetected glitch in the detection electronics, we shouldn't see them preferentially when we're pointing at the Milky Way. But maybe we had an especially unlucky and misleading run of statistics. The probability that this correlation with the galactic plane is due merely to chance is less than 0.5%. Imagine a wall-sized map of the sky, ranging from the North Star at the top to the fainter stars toward which the Earth's South Pole points at the bottom. Snaking across this wall map are the irregular boundaries of the Milky Way. Now, suppose you were blindfolded and asked to throw 5 darts at random at the map, with much of the southern sky inaccessible from Massachusetts declared off limits. You'd have to throw the set of 5 darts more than 200 times before, by accident, you got them to fall as closely within the precincts of the Milky Way as the 5 strongest meta-signals did. Without repeatable signals, though, there's no way we can conclude that we've actually found extraterrestrial intelligence. Or maybe the events we found are caused by some new kind of astrophysical phenomenon, something that nobody has thought of yet, by which not civilizations, but stars or gas clouds or something that do lie in the plane of the Milky Way emit strong signals in bafflingly narrow frequency bands. Let's permit ourselves, though, a moment of extravagant speculation. Let's imagine that all our surviving events are in fact due to radio beacons of other civilizations. Then we can estimate, from how little time we've spent watching each piece of the sky, how many such transmitters there are in the entire Milky Way. The answer is something approaching 1 million. If randomly strewn through space, the nearest of them would be a few hundred light years away, too far for them to have picked up our own TV or radar signals yet. They would not know for another few centuries that a technical civilization had emerged on Earth. The galaxy would be pulsing with life and intelligence, but unless they're busily exploring huge numbers of obscure star systems, they'd be wholly oblivious of what's been happening down here lately. A few centuries from now, after they do hear from us, things might get very interesting. Fortunately, we'd have many generations to prepare. But if, on the other hand, none of our candidate signals is an authentic alien radio beacon, then we're forced to the conclusion that very few civilizations are broadcasting, maybe none, at least at our magic frequencies and strongly enough for us to hear. So consider a civilization like our own, but one which dedicated all its available power, about 10 trillion watts, to broadcasting a beacon signal at one of our magic frequencies and to all directions in space. The meta results would then imply that there are no such civilizations out to 25 light years, a volume that encompasses perhaps a dozen sun-like stars. This is not a very stringent limit. If, in contrast, that civilization were broadcasting directly at our position in space, using an antenna no more advanced than our Arecibo Observatory, then, if Meta has found nothing, it follows that there are no such civilizations anywhere in the Milky Way galaxy. Out of 400 billion stars, not one. But even assuming they'd want to, how would they know to transmit in our direction? Now consider, at the opposite technological extreme, a very advanced civilization, omnidirectionally and extravagantly, broadcasting at a power level 10 trillion times greater. That's 10 to the 26th watts, the entire energy output of a star like the Sun. Then, if the meta results are negative, we can conclude not only that there are no such civilizations in the Milky Way, but none out to 70 million light years. None in M31, the nearest galaxy like our own. None in M33, or the Fornax system, or M81, or the Whirlpool Nebula, or Centaurus A, or the Virgo cluster of galaxies, or the nearest Seifert galaxies. None among any of the 100 trillion stars in thousands of nearby galaxies. Stake through its heart or not, the geocentric conceit stirs again. Of course, it might be a token not of intelligence, but of stupidity to pour so much energy into interstellar and intergalactic communication. Perhaps they have good reasons not to hail all comers. Or perhaps they don't care about civilizations as backward as we are. But still, not one civilization in 100 trillion stars broadcasting with such power on such a frequency. If the meta results are negative, we have set an instructive limit. But whether on the abundance of very advanced civilizations or their communication strategy, we have no way of knowing. Even if Meta has found nothing, a broad middle range remains open. Of abundant civilizations more advanced than we, and broadcasting omnidirectionally at magic frequencies. We would not have heard from them yet. On October 12th, 1992, auspiciously or otherwise, the 500th anniversary of the discovery of America by Christopher Columbus, NASA turned on its new SETI program. At a radio telescope in the Mojave Desert, a search was initiated intended to cover the entire sky systematically. Like Meta, making no guesses about which stars are more likely, but greatly expanding the frequency coverage. At the Arecibo Observatory, an even more sensitive NASA study began that concentrated on promising nearby star systems. When fully operational, the NASA searches would have been able to detect much fainter signals than Meta and look for kinds of signals that Meta could not. The Meta experience reveals a thicket of background static radio interference. Quick re-observation and confirmation of the signal, especially at other independent radio telescopes, is the key to being sure. Horowitz and I gave the NASA scientists the coordinates of our fleeting and enigmatic events. Perhaps they would be able to confirm and clarify our results. The NASA program was also developing new technology, stimulating ideas, exciting schoolchildren. In the eyes of many, it was well worth the $10 million a year, $10 million with an M, dollars a year, being spent on it. But almost exactly a year after authorizing it, Congress pulled the plug on NASA's SETI program. It cost too much, they said. The post-Cold War U.S. defense budget is some 30,000 times larger.
The chief argument of the principal opponent of the NASA SETI program, Senator Richard Bryan of Nevada, was this, from the Congressional Record for September 22, 1993. So far, the NASA SETI program has found nothing. In fact, all the decades of SETI research have found no confirmable signs of extraterrestrial life. Even with the current NASA version of SETI, I do not think many of its scientists will be willing to guarantee that we are likely to see any tangible results in the foreseeable future. Scientific research rarely, if ever, offers guarantees of success, and I understand that. And the full benefits of such research are often unknown until very late in the process, and I accept that as well. In the case of SETI, however, the chances of success are so remote, and the likely benefits of the program are so limited that there is little justification for $12 million taxpayer dollars to be expended for this program.